So this afternoon I also put in the Chapter 6 stuff into the OneNote, so that's all there for you. We have 2 homework assignments remaining. The stuff that is due this week, so the Chapter 5, the worksheet, and the review, and then whatever Chapter 6 stuff we assign. Now keep in mind, if you've done all the homework to this point, the last homework grade is dropped. So do you really need to do the Chapter 6 homework in a way that has to be turned in? If you've done all your other homework assignments and there's still a homework grade to be dropped, do you really need to worry about doing all of the Chapter 6 homework before or by the due date? No, right? A lot of you guys are really busy right now. I know there's lots of things happening, lots of tests and projects and whatever's going on. So keep that in mind, right? It's part of the reason why I don't put the drop in until the end.
I don't understand. So,
What do you mean you don't understand? If you do all the homework assignments, what's being dropped?
Yeah, okay, I understand that part.
Okay.
But let's say that I don't do any of the chapter 6 problems.
Yeah.
You'll still drop that, like all as one.
Yeah.
Oh.
Yeah. When I say homework, it's like a homework assignment, like in the grade book.
Whole chapter 6.
Well, it's not going to have any more chances than one more time to check homework, right?
Yeah.
There's just 2 more Sundays before the end of the semester.
Okay.
So, yeah.
I don't know that, please.
Sure, you can walk even.
Oh, thanks.
So, unless it's an emergency, in which case you should run.
No, I'm good. Thank
Okay.
you.
Okay. So, I have a couple of things that I noticed when grading the Chapter 5 tests that we need to talk about, because these were mistakes I saw large portions of the class make. So we definitely need to spend a moment and kind of review some algebra concepts. So let's look at this first one. Let's say we have this expression. Can I do this to reduce? No. 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 How many times did I see you guys doing things like this on your Chapter 5 test? I saw large portions of the class reducing like this on multiple occasions. Why is this not okay? Imagine if you just had this as numbers, right? This should be 3 over 2. If you reduce like that, what do we get? You get 2, right? Or you could say even 1, even worse, right? You want to do some currency exchange? You give me $2, I'll give you back $3.50 or $3.50, or I'm sorry, $1.50, right? Let's just keep doing that. If you believe that you can reduce this way, how do you have to reduce that? How do I reduce this? This can be reduced. What? Take out an x from the numerator, right? You factor. Now that it's in a place where it's all multiplication, now you can reduce. Right? So this reduces to y plus 1 over y. Right? Does it matter if I write x's and y's or if I write this as like sine x times cosine x plus sine x over sine x times cosine x? Is it still the same problem if just x is cosine x and y is cosine x? No, it's still the same problem, right? Doesn't matter if it's x's and y's or sines and cosines. You guys agree? If you're considering doing some reducing, try rewriting it in a form where it's just like a little bit more obvious what's going on, where you don't have all the sines and cosines and stuff in the way, right? Or even better, write it with numbers and go, if I reduce like this, does the fraction still equal what it's supposed to equal? You know what I mean? Did you guys get it? It's a critically important skill that you're able to kind of do this correctly, consistently. It will get in your way in all of your future math classes if you're not able to break that habit now. Let's break it! You know? Okay. To solve this, what do? We divide both sides by x, right? Who says yes? You're looking at me like, yeah, that's what I want to do, but clearly I shouldn't do that because the last time you suggested the thing to do is not what you wanted me to say yes to. No, you can't do that. Why not? You lost solutions by doing this. Y equals 1 is an answer, but it's not the only answers. You're missing solutions now. Clearly, if x equals 0, that should be a solution, right? 0 times y should equal 0. You guys see that? What should I have done to solve this? Yeah, subtract the x to the other side. And then what? And then we factor. Then you apply the zero product property, and you solve just like you would have a polynomial way back in Algebra 2, right? Does that ring some bells? You see that this solution, when we divided by x, you missed. Unrecoverable if you divide by variable to get those solutions back. They'll be gone forever. You'll never find them, which is sad. Okay. Last one. No! It's multiplication.
That's my bad. Put over 1.
It's not 5x over 5y.
No, 5x.
I saw this multiple times from lots of really smart people, where sine x times like cosine x over sine x became sine times cosine over sine squared. Ah, it just makes me cry. That was embarrassing. Okay, so again, these are prior algebra skills. Okay, just slow down, be careful is the moral of the story. Slow down and be careful. I know you guys know these things, right? When I show you it, it's like, oh yeah, I know that. And then you get to the test and you stress out and you do something silly because you just didn't slow down and just think about what you're doing. Like, strip away the sines and cosines and all that nonsense and just think about it like a normal algebra problem. Like, strip away the trigonometry parts and try rewriting it that way and go, can I do what I'm about to do? Right? Just be careful. All right. Today, we're going to talk about section 6.1, which is about sum and difference identities. So what we're going to do to start is we're going to derive all of these sum and difference identities today. The first one's rough, but once we have one of them, we can do some clever substitution and just do the rest of these proofs algebraically. But the first derivation gets a little complicated. So what we want to find is figure out how we can rewrite cosine u minus cosine v. That's what our goal here initially is going to be. I'm going to give you a hint right now. It's not going to be cosine u minus cosine v. Trig functions do not distribute. What is the only operations that you know that distribute?
Like in general?
Yeah.
Multiplication.
Multiplication and division. That's it. If you try to distribute an exponent, you're wrong. If you try to distribute a radical, you're wrong. If you try to distribute a logarithm, you're wrong. If you try to distribute a trig function, you're wrong. The only things that distribute that you know about are multiplication and division. Just as an aside. Okay. So, well, okay, I want to figure out what this equals. What do I do? Well, I got to go back to basics here. So what does that mean? Come on. Going back to our good old friend, the unit circle. I'm just going to kind of eyeball this. All right. So let's say that we have some angle here that we'll call V. And we have some other angle here that we'll call U. So this spot here is the angle U minus V. Everybody agree with that? Sure. What is that point? What does the coordinate for that point have to be? We're on the unit circle. This is like chapter 2 stuff.
Radius.
The coordinate for the point is radius? Okay, that's fair.
It is slightly bigger now.
I mean, it's cosine V, comma, sine V, right? It's a point on the unit circle, right? What's this point have to be? The blue one.
U.
U.
Or whatever.
Same idea, yes. Okay. So if I call this point here point A, and this point here point B, what I'm interested in is going to be translating this now So because I have this little acute angle here. I just want the circle. There we go. That's something. Translating this point, or this circle now, or this angle, I should say, so that my point B is here, and my point A is here, and this distance between them I'll call theta, is the same here. God bless you. So what's the coordinate at this point B prime that I drew? Oh, come on, guys. It's on the unit circle. 1, 0. Yeah. And what's the point or the coordinate for A prime? Cosine theta, sine theta. Right? Everybody's okay? Note here, what is theta equal? That's u minus v, right? Okay. So for me to be able to do this, if I know these 2 points, or if I know point B anyways, I need to work out so that this distance here and this distance here are the same, right? If I've done this translation correctly, the length of segment AB needs to be the same as the length of segment A prime, B prime. Everybody agree with that? Okay. How do I calculate the length of something given 2 points? Distance formula, great. So how do I calculate the distance of AB? There's my 2 points. Okay, good. Square root of.
Was it x plus y squared minus
Cosine V
okay.
minus cosine U squared plus sine V minus sine U squared. Now, what if I do the same thing for A prime, B prime? So square root of cosine theta minus 1 squared plus, oh, what are we doing here? No. It's 1 minus cosine. right? You always take the further point first.
What do you mean by like further?
Well, like I use the B point first. If we're taking the length from A to B, right?
Yeah.
So it's like x2 minus x1, right?
Okay.
So the B prime is the x2, right? Okay, that's what I mean. All right, so we got this. So to get our equation, what I need to do is get cosine theta, which is the same as cosine u minus v, by itself on one side. Everybody's okay with that? And that should be the only theta left in the whole darn thing. What do you want to do first?
Square both sides to get like the square root.
I love it. Okay? So we do that, square roots are gone. What do you do next?
Can you distribute the cosine? And FOIL?
How about we start by foiling? You can't distribute into a foil.
Okay.
So what do I get when I do cosine v minus sine or cosine u squared like that? Cosine squared v minus 2 cosine v cosine u plus cosine squared u. Everybody agree with that? And we'll do the same thing. So I get sine squared v minus 2 sine v sine u plus sine squared u. And then we'll do the same thing. We'll FOIL out 1 minus cosine squared. So it's going to be 1 minus 2 cosine theta plus cosine squared theta. And then what about 0 minus sine squared? What's that? Yeah, just sine squared, right? Yeah, baby. Oof, that got long. All right, what do you want to do now? What should we do now?
Do you like make the cosine squared u and the sine squared u like go together and make it one?
Yeah, let's do that. So that's a 1. Do we have any others? How about cosine squared v and sine squared v? That's a 1. What else? I have a cosine squared theta and a sine squared theta. That's a 1. That's a 1. Is everybody okay with what we did there? Now what do you want to try? Let's do this. How about that? I like that a little better, don't you? You could add the ones together, but like, I'm just going to keep subtracting one from both sides and just get rid of them all together. That's even better, right? Sure, 1 plus 1 is 2. Yeah, fine. Then subtract 2 from both sides. Still the same thing I'm doing. What do you want to do next? Again, the goal is to get cosine theta by itself, where that's the only theta. Are we almost there?
Oh, you just divide by negative.
Yeah. So what do we have left? We have cosine v cosine u minus sine v times sine u equals cosine theta, which is cosine of u minus v. And that is our first identity.
Why is it minus still? You're getting rid of the negative 2.
Oh, thank you. Plus. Good call. Great attention for detail. I love it. A true mathematician there, nitpicking all the details. I love it. All right. You ready to do the next one? I can do this in one line. I don't have to draw any pictures. How is Mr. Kulik going to do this? Adding is the same thing as subtracting a negative, right? Well, now I can just use my formula from before. My odd-even identity says cosine of negative v is just cosine v. My odd-even identity says sine of negative v is negative sine v. So there we go. Done. That was a lot faster than the previous proof, Mr. Kulik. Well, yeah, that's because I had this like really excellent formula already derived that I could use. So in general here, the typical way we would write this, or write them both at the same time, is this way. So this is both the sum and difference identity written in one line. Notice here when we write this, I wrote plus minus here, but I wrote minus plus over there. What does that mean? Basically, you read the top symbols together. Cosine u plus v is going to be the cosine u cosine v minus sine u sine v. And if I wanted cosine u minus v, I'd read the bottom symbol, cosine u times cosine v plus sine u sine v. Right? We've just written both formulas together in one line. Let me zoom a little bit. That's what I mean. Rita.
So on this thing you like did like right before, I don't really do like cosine, like you do times cosine and the there.
I used the identity. I use this.
Oh.
Right? What is this? Is cosine u minus v. Right? So I used the identity that we just derived, except I plugged in negative v everywhere there's a v. Right? Sure! So we could use this to like do identity things like we've been doing, but we can also do it to evaluate and get exact values for angles in a way we haven't been able to before, or with angles we haven't been able to do before. Let's say we want to find the exact value of cosine 75. What does exact value mean? No decimals. Yes, I must be using the unit circle in here at some point. Absolutely correct. Great. So, what am I going to do? I'm going to find a way to rewrite cosine, or 75, I should say, as the sum or difference of two unit circle angles. So if you wanted to do addition, that's usually what I like to do. What two unit circle angles add to give me 75? The fact that we're waiting this long to answer is concerning to me. What two unit circle angles will add to give me 75? 30 and 45. We'll just, these were in degrees, so you could just give me degrees. You don't have to give me radians. It's okay. Now, these guys are both on my unit circle. That's the key. I can't do 74 and 1. That doesn't help me any because those are not unit circle angles. So, what do I say? I say cosine of 75. Well, that's the same thing as cosine of 30 plus cosine of 45. So I apply my formula, the up above that we just derived, cosine 30 times cosine 45 minus sine 30 times sine 45. Everybody okay with that? Now I'm going to go to my unit circle and look up the value for cosine of 30. That is the square root of 3 over 2. I'll look up the value for cosine of 45. Square root 2 over 2. I'll look up the value for sine 30. That's 1/2. And then sine 45, that's square root 2 over 2. So when I put those all together, I get square root 6 over 4 minus square root 2 over 4. So how do I write that final answer then? Those have a common denominator, right? Do I write that as square root 4 over 4? And then simplify down to 1/2? No! So you would be telling me then that radicals distribute, right? Which they do not. So what do I write as my final answer? Yeah, I just write it like that. Oh, Mr. Kulik, you got me. You got me. You tricked me. Yeah, I thought it was going to be something. And I was like, no, there's no thing. It just, you write them next to each other. But I need to say it because it's really tempting to just go, oh, 6 minus 4, that, or 6 minus 2, that's 4. Right? So we need to make a big deal out of it because it's easy for you wanting, or to want that to be true. All right. Let's do sine of u plus v. All right, how am I going to do sine of u plus v without having to go back to the unit circle and redrawing this thing? What angle sum identities do I know? I know them for cosine, correct? So how can I rewrite sine as a cosine? Well, let's say this first. Let's call this just sine theta. I'll use my cofunction identity to rewrite it that way. Everybody's okay with that? And then we're saying theta is the same thing as u plus v. I'll distribute through my negative, just some piddly little algebraing. And now I'm going to regroup this stuff together. So I'm going to call pi over 2 minus u one angle and v the other angle. What do I have here? I have the cosine of the difference of two angles, right? I'm just going to think about that as one thing. Why is it going to be convenient to think about that as one thing? Because I can use the cofunction identities afterwards just to get rid of them, right? I don't have to do another angle difference, which is lovely. Okay, so I get cosine of pi over 2 minus u times cosine of v plus sine pi over 2 minus u times sine of v. Cosine of pi over 2 minus u is just sine u. Sine of pi over 2 minus u is just cosine u. So what do we have here? I have the sum of two angles for sine. Katie. Sure. Oops, did I start? Oh yeah, I did start with sum. Rita.
Wait, how do you know, like when you wrote it as an identity, how do you know it's like a plus between that and that line?
So when I read the identity, I did cosine minus, so I need a plus.
Oh, that's what you're trying to say.
Yeah.
Is that last sign, the 1 point answer, is that?
So my u's are going to have tails. My v's won't. Even if the v's start getting roundy, they won't have a tail. The u's will always have a tail. I know, I have a hard time telling my u's and v's apart. That's how I do it. Is the u's all get tails. I'll never make a u like this, because that's a union symbol.
Yeah.
My u's all have tails. Big u's, little u's, any u's, they all get tails. All right, what if I want to do sine of u minus v? How would I do that?
Can't you just write the same with the minus sign?
No, but I can do it as plus a negative v, and then use my formula from above. I mean, it's going to turn out to be that, but like you can't just assume it's going to turn out to be that. You have to prove it, right? That's what we're doing. We're proving all of these identities. Isn't this wonderful? I'm having a grand old time. Can you tell? So there it is. So just like before, what am I going to do? I'm going to write them together in one statement because I'm a mathematician and I'm inherently efficient. So why take 2 lines to write something when I only need 1? And now, just like before, we'll do another example. Oh no, Mr. Kulik. 5 pi over 12? How am I supposed to break up a fraction into unit circle angles? Take a deep breath for me. On the unit circle, what is the denominator of any unit circle angle? There's 2, 3, 4, and 6. Those are all factors of 12, yes. So if I want to break this up, the 12 needs to reduce to get to a unit circle angle, right? So how can I break up 5 into 2 numbers that'll reduce when I divide, or when I have them as over 12s? 2 and 3, right? Everybody agree with that? Everybody agree that's the way you'd want to do it? So it turns into pi over 6, yay! And pi over 4, yay! Unit circle angles, right? All I needed to do was make sure that 5 broke up in a way that those guys would reduce, right? Looked scary, but really not so scary. Okay. So I can say sine of 5 pi over 12 is equal to sine of pi over 6 plus pi over 4. I apply my formula from above. It tells me I have sine of pi over 6 times cosine of pi over 4 plus sine of, I wrote cosine first. Okay, cosine of pi over 6 sine of pi over 4. I go to my unit circle. Sine of pi over 6 is root 3 over 2. Cosine of pi over 4 is 2 over 2. Cosine of pi over 6 is 1/2. Oh, I'm sorry, that's reversed, right? This one is the 1/2, and this one is the root 3 over 2. And then that's root 2 over 2 still. And what do I get? Root 2 over 4 plus root 6 over 4. Or, how do I write this? Square root 8 over 4, right? No. Thank you. Thank you for almost laughing as I said it. It's like, no. No, you silly goose. All right. Now, how are we going to do tangent? Here, it's so easy. Oops. Tangent is sine over cosine, right? Now we just plug in the formula. Oops. Okay, so you could write it that way. Does that look familiar to anyone?
No.
Yes.
It should. All right, Mr. Kulik, where? See that? Is that the same thing? Guess what the more common way of writing the angle sum for tangent is? That one. Why do you think we did this proof way back then? So we don't have to do it now. Right? Yay! Isn't that cool? I love it when stuff from the last chapter is like the answer to stuff in the next chapter. It's like, oh, we already did that?
Yeah, that's like my favorite thing about these two.
Right? It's like, oh, look at me. I'm already a step ahead. I can sense the sarcasm, by the way. Like, it was not lost on me. I get excited. Excuse me. All right. So again, let's compact this together now. Bloop. And again, I'll write the plus or minus version because we're at this point, you get the idea with putting the negative sign in to do u minus v, right? Sophia.
I just want to make sure. So for the sign, was it like if it's negative, if it's like u minus v, then in the answer is going to be subtraction, right?
No. So the way you read it is if you're doing like tangent of u plus v,
Yeah.
you have a plus on top, but you have minus on bottom. If you're doing tan of u minus v, you have a minus on top, but the plus on bottom.
Okay, then for like, can we go to sign? So if it's sign on top, it's sign, or if it's plus on top, it's plus on top.
Mm-hmm.
Okay.
Right? That's the way you read these formulas. Does that feel okay? Okay. All right. Where did that just plop in? Yes, of course. All right. So it says, write each of the following expressions as a single trigonometric expression. So what do I do here? Well, if I look at this, what I see is sine u times cosine v minus cosine u sine v, right? That's the form of sine of u plus v so that's just sine 70. because I have like sine u times cosine v minus cosine u sine v. That is exactly sine of u plus v. So I just used the formula in reverse. Does that feel okay?
Then why isn't it negative?
Oh, yeah, sure. Thanks. Good eye for detail. How about B? So that's going to be tan of u plus v, right? You guys agree? And then this last one, that's cosine of u minus v. Uh-oh. What do I need to do to subtract 3 pi over 7 from pi over 5? Oh, yeah, common denominator. What would the common denominator here be? 35. So I'm going to have times 5 to the first fraction times 7 to the second fraction. So 15 pi minus 35 pi. Nope, dummy. 7 pi all over 35. I was one step ahead of myself. So that's just going to be 8 pi over 35. What do you guys think? Okay on that? Okay. Again, pretty straightforward. You're just using the formula, right? Let's do some proofs. I'm excited to do this. Look at these cool ones here. All right. What side do you want to work on? The left or the right? Hey, focus! I mean, it should be obvious. I mean, look at what we've been doing. We want to start on the left side. And then what do we use? The angle difference formula for cosines. Everybody's cool? I go to the unit circle. What is cosine of pi over 2? 0. What is sine of pi? 1. Oh. There it is. So easy. sine x minus pi. We'll do the same thing. So I have sine of x times cosine pi plus, minus sine of pi times cosine x. I go to my unit circle. What is cosine of pi? It's -1. Sine of pi is 0. And oh, there it is, negative sine x. Oh, so easy. It was a good joke, though. Just kidding. I was teasing Ava. I was just joking.
Oh, sorry, yeah.
That was me just joking. All right. This last one, not quite so trivial.
Yeah. I'm so sorry. It's okay. It happens a lot.
It is not that word.
All right. This one, not nearly so trivial. Which side should I start with? Yeah, for sure. Why?
That was more complicated.
The 3x is the thing that scares me. So what am I going to do with the 3x? I'm going to write it as 2x plus x. Ah, nice. Well, so now I can use an angle, one of my formula, my identities. What was I going to do with the 3x? And have anything I could do with that? I got to get rid of it. Got to turn it into a 2x somehow. This will get rid of all the 3x's and turn it into 2x's. Okay, so I do my cosine formula. So I have cosine 2x times cosine x minus sine 2x sine x So I look here now. I got half of what I'm supposed to. You guys see that? Yeah. But I got all this extra stuff here. Here's the trick. Where am I going to use my second angle sum or difference formula at? I'm going to use it here. How do I write that as a sum or difference formula? This is tricky. How am I going to rewrite cosine x as an angle sum or difference formula? I'm going to write it as 2x minus x. Why would I want to do that? Right. And when I use this identity, what am I going to get? I'm going to get a cosine 2x times cosine x. Hey, there's the other one of those that I needed. And I'm going to get a plus sine 2x sine x. And hey, look at that. Add those two guys together. Bada bing, bada boom. We are home free. Now you might have asked, or you might have thought, Mr. Kulik, couldn't I have just taken sine 2x and written that as cosine x, or sine x plus sine of x plus x, and done the angle sum formula for that? Yeah, you could. It's not really helping us get to the answer though, because we still need another cosine 2x tumbling out of this somehow, and that ain't gonna get you any more cosine 2x's. So it's a tricky one because you had to do that.
How can you just make cosine x the 2x plus x?
Well, 2x minus x is x, right?
Yeah. Oh, sorry, I didn't. Sorry. Yeah. Okay.
It's okay. All right. So one special variation, one specific case of these angle sum formulas would be when I have a situation like this. Right? Where I'm just adding the same thing together. If I apply my angle sum formula, I get this special case identity. We call that the double angle identity. We could derive the other, these other double angle identities in much the same way. In the interest of time, I'm not going to do that right now because I feel like we've had enough deriving for the day. The thing to remember here, the thing that I want to point out is that all of these double angle identities are just special cases of the angle sum and difference identities, right? They're just sine of 2u is just sine of u plus u. Cosine of 2u is the same as cosine of u plus u. Tan of 2u is the same as tan of u plus u. So it's just, these are just a special case of the angle sum formulas where both angles are the same. Let's do an example of how we can use this. Oh, never mind, I did that example already. Oh, that feels like a good place to stop. Don't you guys agree? It's quitting time here for today. What is the numbers that I wanted you guys to do here? They always seem so excited, don't they? So, again, the chapter 6 problem set is up. I also put in the review packet that I would have given if we had a time to do a chapter 6 test, which we don't. That's up. So again, you can work on any or all parts of that. The chapter 6 problem set will be due not this Sunday, but next Sunday. It'll be all of the chapter 6 problems. I know.
Will the final be like more of chapter 6 than any other chapter? Does it have on it?
No,
Okay.
probably an even distribution is kind of what I would be thinking.
Can I see my chapter 5?